So, we will do another instability which is on rotating convection. Okay. So, I will show you okay, basically patterns, linear pattern, well basically pattern, do not worry about pattern, it is just instability. So, I have put rotation, so my Navier-Stokes equation will have one more term, is a Coriolis force. So, it is a linear system, so our nonlinear term is off, and we got this is the buoyancy. So, these two terms and these three terms are exactly same as before. I am adding Coriolis, C for Coriolis, and theta does not get any other contribution for rotation, only the velocity field gets contribution Fc. So, theta remains exactly same. So, I am adding new term Fc, Coriolis force, and what that is, this Bushnell del dot d is 0. So, Fc I need to non-dimensionalize. Remember, this was the whole equation was non-dimensionalized. So, what is Coriolis force? Minus 2 omega cross u. So, and this is the derivation you can look at. So, my velocity field is non-dimensional is doing kappa by d. So, this u is non-dimensional, and I divide by k squared kappa squared by d cube. So, this whole thing is divided. So, what I finally get is that 2 omega d squared by kappa z hat, z direction, cross u, because omega is along z direction. So, my fluid is rotating about z axis with rotation frequency omega. Okay. So, this is, you can think of a cylinder which is heated from the bottom and cooled from the top. Actually, we are doing a box only, no cylinder. Okay. So, I am sorry, this is a box which is rotating with omega frequency about z axis, and gravity is also along z downward. So, now it in fact is very straightforward, the derivation. This is beauty of Kriya-Haring. So, you do not need to do much. I need to resolve this one along Kriya-Haring, right, because this one I already have done it. I mean, this you have seen in your notes, this we have already done. So, I need to resolve this one. Now, z hat I know in Kriya-Haring how it looks like, right. It has component u2, e2 and e3. So, but before I go on, I just want to define one non-dimensional number. Okay. So, this object in front, now this Microsoft. So, this object in front is Prandtl times square root Taylor number. Ta is called Taylor number, okay, or if I use another definition, this is called Ekman number. So, Taylor and Ekman are related with rotation. Now, for this lecture I will not really go too much into detail of this stuff. So, this number is exactly same as Prandtl square root Taylor. So, Taylor is omega squared, not omega. So, I have omega, that is why I take square root. So, 4 omega squared d4 by nu squared. So, that is called Taylor number. So, non-dimensional numbers are useful. I will probably emphasize towards the end of this lecture. Well, let me just tell you right now why non-dimensional numbers. So, Rayleigh critical, the 657 is fixed irrespective of what fluid you use or what temperature I am heating at the bottom, top. So, for any experiment you can compute Rayleigh number and see whether it is above Rayleigh critical. So, it is independent of your experimental conditions of fluid or plates, as long as free slip boundary condition works, great, you just Rayleigh is what is important. Okay. So, if I increase my box size by double, but my temperature difference is triple, does not matter, you do not need to compute, just compute Rayleigh critical. Same thing for Taylor number, you do not need to worry about what omega, what box size, compute the Taylor number and I will get a condition for instability. So, you can see the power of non-dimensionalization. You do not need to work out this instability condition for system specific values. An Ekman number is defined as this. Okay, these are just quantities. Now, so now this is my equation in terms of I have missed here this k, uk. So, this equation is not fitting here. Okay. Now, So, this one I already have computed in terms of Cray Herring. This one can also be computed on Cray Herring, but it is cross. So, this has need some labor. I will not do it here, but this we need to resolve. So, this will be E3 and E2 and cross U2 and U1, U2 U2 plus U1 U1, right. So, this I will leave it for you to do it, right. I mean, they are just cross products, and just remember that E1 E2 E3 are cyclic and straightforward. It is a bit of algebra, but it can be done easily. So, this equation we get. Now, U1 will not decay. So, now of course, I have to tell you what is A. A is this matrix. So, I have U1, U2, theta, all three of them there now, and A is this matrix. Earlier, my U1 was basically these two guys were 0. Remember this one? Again, not remember. This was not there before. So how do we remember? So, Taylor number 0 will give you this one is decoupled. If I set Taylor 0, this will decouple. So, U1 will decay. Now, because of Taylor number being non-zero, this will not decay. It is a positive feedback. Okay. Now, so Taylor number is coupling U1 and U2. Do you see that? Because without Taylor number, U1 was decoupled and decayed because of viscosity. But now this will remain. This will be playing a role in instability. Now you can do the. I will just ask you, if I remove Taylor number, you can easily see that you will get this is same as before. Now, one important point I want to tell, that if you had only rotation but no convection, then which terms will go away? So, by the PR will remain there as a viscous term. Okay. So, these two terms will non-zero, and these term, well, theta of course does not exist, only rotation. So, I just take a fluid and rotate it. So, this will be U1 and U2, this box. So, the diagonal term will be coming from viscosity term, and that will decay, and these two terms are what will they give you? I am not doing this. So, let us put viscosity to 0, and this is alpha and minus alpha. What does it give you? Alpha and minus alpha. So, what are the eigenvalues for this? So, trace is 0 and determinant is alpha squared. So, trace 0 means there must be a imaginary complex conjugate of each other, and your determinant is positive, right, alpha squared. So, it is plus I omega and minus I omega. So, these are oscillations, right. I mean, you can easily see this from the structure of the matrix. So, these are called waves. In fact, they have a name. This is called internal gravity waves. Okay. Not gravity waves, inertial waves. For rotation, this for gravity, this is called inertial waves. Okay. For rotation, is called inertial waves. And the property of the waves, I am not asking you to do it for this course, but you can read in this book. So, very briefly, I discuss about these waves. Okay. It has a role in the instability. Well, I am going to give that as a homework. Is that clear? So, we can disentangle from the matrix. So, there is a part which is oscillations, there is a part which is coming, which can convection will give you instability, which is will try to create rolls, but because of the oscillations, it will try to make oscillatory instability. Okay. Now, I need to worry about eigenvalues and eigenvectors of this. Okay. And once let us look at the eigenvalues. Now, this matrix is not easy to, this 3 by 3 matrix. Now, I can't get all the 3 eigenvectors and eigenvalues by hand, which I could do for 2 by 2, but this one I can't. So, I can look only for neutral stability. So, how do we get neutral stability? So, 0 eigenvalue. So, what do I get 0 eigenvalue, by the way? The condition for 0 eigenvalue is determinant is 0. the easy part. Determinant is product of the eigenvalues. So, determinant being 0 will give you one of the eigenvalue must be 0, and I do not even know what the other two guys are, but I know one of them are 0. The trace is negative, so at least one of them is negative for sure, okay. But this is what I have left it as a very crude analysis right now, that I just set determinant to be 0 will give you neutral, will give you one of the eigenvalues negative, one of the eigenvalue is 0, one of them is at least has a negative part, but this is a condition for lambda equal to 0, and this will give you Rayleigh critical given Taylor number, right. So, this is, by the way, I immediately put Rayleigh as Rayleigh critical for lambda equal to 0. So, when I see Rayleigh critical, that means lambda equal to 0. So, that gives you in terms of Taylor number. Now, S is non-dimensional number k per n pi squared, okay. So, given k per n Taylor number, I can get Rayleigh critical, okay. So, it depends. Rayleigh critical is not for given n is not some 27 pi 4 by 4, it depends on Taylor number. And if you want to get for what k per will Rayleigh critical be minimum, we need to analyze this further, you know. So, I am not, so these are, I am going to leave that as a homework. So, eigenvector for lambda equal to 0 I can find, I can't find for others by hand. So, eigenvector for lambda equal to 0 is this. So, remember this was u2, I should not write u2 and theta. Before these two were non-zero and u1 was going to 0, but now u1 is not 0. So, u1 and u2 both are non-zero, okay. So, that means it is a 3D structure, it is not a 2D structure like earlier case. Now, I have plotted for a very crude example for one special case, this coming from Chandrasekhar's book. Now, it has both u1 and u2, you see this is u1 and this is u2, okay. This comes from these conditions, and the structure not very, I am not very happy with this diagram, but it is a 3D structure, it is like some kind of roll which is twisting. So, what I would like you to do is using computer program. So, that is why either Mathematica or Maple or MATLAB or SymPy, get all the 3 eigenvalues, 3 eigenvectors, eigenvalues first. Is it, so we have the lambda equal to 0. Now, what are the eigenvalues? Now, this lambda equal to 0 is at the transition. Now, if you go slightly above Rayleigh critical, so Rayleigh increase to beyond Rayleigh critical, then does it remain real or does it become complex? Is the question clear? So, this matrix A. So, I know that for Rayleigh equal to Rayleigh critical, one of the eigenvalue which is likely to become unstable is lambda equal to 0. So, when Rayleigh becomes greater than Rayleigh critical, I can plug in this, no, this Rayleigh is sitting here, where is Rayleigh, this guy. So, compute the eigenvalues. Now, will it become complex or will it remain real? You can do it on computer, no. So, I like to see the nature of eigenvalue, and that will tell you whether it is oscillatory or stationary, and get the eigenvector, and we should analyze it this structure better, okay. So, I will stop here, thank you.